Loch Nahannigan has lain at the foot of Turlough Hill in County Wicklow since the last ice age left its prints on Ireland. The natural lake has a companion now, a man-made reservoir on the peak of the hill. The two together form the hydraulic elements of the pumped storage system at Turlough Hill. The function of Turlough Hill Pump Storage Station is to provide extra energy to the national system when it is most needed. When the station is supplying energy, water flows down a pressure shaft inside the mountain and through turbines situated in a cavern hollowed out of the rock. Electrical energy flows out to the networks. Water flows out through a tail race to the lake. During the night, when the load on conventional power stations is very low, energy is drawn into the Turlock plant. At the press of a button, the turbines become pumps. Water is pumped back from the lake to the reservoir, ready for use again the next day. The electrical storage capacity is 1,500 megawatt hours. Turlough Hill may be described as a pure pump storage scheme since it is entirely self-contained. There is very little natural inflow to the upper reservoir, which makes it independent of seasonal or other variations. There is, of course, a loss of electrical energy in the course of the daily cycle. The maximum overall efficiency of the station is about 75%. To understand how the loss is more than compensated for, consider how Ireland's daily demand is met by hydro stations and by thermal stations burning oil, turf, and native coal. These may be grouped into power blocks. Starting with the block which is most economic in providing energy, the rest successively less so. The upper layers will be the first to be cut out when demand falls, as it does during the night, while during the day, demand fluctuates to high peaks. Now consider the effect of Turlough Hill. First, during the night, when pumping load keeps the most economic stations in operation and thus avoids problems involved in shutting down and restarting thermal plant, which can now be run continuously at a maximum efficiency. The resultant gain offsets the loss involved in the pumped storage. During the day, the generating power of the station takes care of the peaks. Here, the advantage of a pump storage system is its remarkable flexibility, combined with minimum cost. Ireland is suited for pumped storage schemes. It has plenty of hills and vales. After surveys of many sites, Turlough Hill emerged a clear winner for several reasons. The subsequent detailed planning by ESB staff covered the overall layout of the scheme with particular attention to areas on the surface and their impact on this high amenity area. Other major considerations were the geological, hydraulic, and mechanical aspects of the proposed site levels. Also, the general configuration and construction of the lakes, the pressure shaft, the tail race tunnel, and the design detail of the mechanical and electrical plant. A natural lower reservoir was available in Loch Nahannigan. As the capacity of the lakes was greater than needed, the level was actually reduced by 14 meters to increase the overall head of water by that amount, to a peak large enough and flat enough in the original state to accommodate an upper reservoir. The small distance to height ratio, only 2.3 to 1, was an advantage because it minimized the length of pressure shaft required. The Turlough Hill site had another advantage in being close to Dublin, a major centre of load demand, and close to the East Coast thermal stations. But there were disadvantages too. The height above sea level, almost 700 metres, meant the risk of costly delays due to the weather. And the position of the site in a high amenity area involved heavy expenditure for environmental reasons. The required electrical storage capacity of the project dictated the size of the upper reservoir. Other factors were the physical limitations of the site, the capacity of the generating plant selected, and their pumping capacity, especially as more megawatt hours are needed to pump than can be produced in output. Another factor is that the gross head of water should not vary by more than 10%, since any greater variation would make pumping inefficient and costly. These considerations suggested a capacity of about 1.3 gigawatt hours. However, since it was possible to add a little additional storage at around the same cost, a capacity of 1.5 gigawatt hours was finally chosen. Water is drawn from the upper reservoir into the pressure shaft and hence to the power station below through an intake structure of reinforced concrete. The tower above it is provided with access from the embankment by means of a tubular steel bridge designed for stability in high wind conditions. The finished tower is 39 meters high with an overall weight of some 5,000 tons and a safety factor of 1.4 against uplift when the interior is empty of water. The bellmouth of the intake is subdivided into 12 channels by guide walls, tapered in every plane. These were designed after model tests to ensure uniform flow. The ratio of throat sectional area to shaft area was a critical factor. Because of the high velocities, the sill, heads, and piers have steel nosing fixed to anchors in the primary concrete, backfilled with secondary concrete through holes cut in the nosings. The intake channels are protected by 40mm screens to prevent the entry of large foreign objects which might damage the pressure conduit, not to mention the valves and turbines down below. A silt trap collects small stones, etc. The tower contains a servo motor which lowers and raises a cylindrical gate so designed that it can be closed even at maximum flow, an operation which is performed automatically in a case of emergency. The hoisting and braking system is hydraulic. Of course, the structure must also act as an outlet to the reservoir during the pumping operation. A major feature of a pump storage scheme is the excavation needed to provide a cavern for the generating hall, together with all the ancillary tunnels shown here in a plan view of the site. Vertical location is determined by the need for a head of water from the lake to prime the turbines when they are acting as pumps. Hence, a low level is required. A generating hall built in the lakeside creates many engineering problems connected with underwater construction, the anchorage of the pressure shaft, and the buoyancy caused by the surrounding water, as well as more amenity problems. For all these reasons, an excavated cavern is the better engineering solution, and on balance is more economical. The location of the cavern naturally affects the design of the pressure shaft. The penstock, 4.8 meters in diameter, narrows to 3.4 meters at the lower end, where it joins 4 manifolds which convey the high pressure supply to the turbines. Each manifold is 2.4 meters in diameter, and each brings reactions of 2,200 tons into the rock. The excavation was carried out from a construction chamber at the foot of the sloping section, while the vertical section was drilled downward from the floor of the reservoir. The penstock lining is formed of low-carbon silicon manganese steel with a wall thickness varying from 14 to 43 millimeters, plus up to 140 millimeters reinforcement in some places. All components were subject to rigorous chemical analysis and distortion tests. Each section, 10 meters in length, was welded on site from 8 semicircular plates. These double automatic welds were checked ultrasonically using radiography as well when in doubt. The sections, the heaviest weighing 48 tons, were lowered in turn through the intake. The total penstock weight is about 2,500 tons. At the foot of the vertical shaft, each section was placed on rails embedded in a concrete floor in the sloping shaft and was then lowered to meet the previous section. Great care was taken in welding within the shaft to avoid distortions. 4 welders inside the section worked in a symmetrical pattern around the circumference of the joints against backing rings. Each 2 sections, when welded, were backfilled with concrete. Subsequently, contact grouting between the steel and the concrete was done through specially designed and positioned plug holes in the liner to ensure that any gaps would be reduced to the design allowances for external pressure forces caused by groundwater head. A case is on record where a rapidly emptying pressure shaft collapsed under the external pressure force and put the plant out of action for a year. To avoid any such disaster at Turlough Hill, external pressure design loads took into account groundwater heads maximized to the level of the upper reservoir. Internal pressure allowed for included testing the manifolds, which are in the highest pressure zone, to 45 kilograms per square centimeter, and this was done successfully. The interior was sandblasted and protected against corrosion with coats of zinc-rich primer and coal tar epoxy. As a backup precaution against external pressure, small pressure relief valves were fitted in the holes used for backfilling. The tail race tunnel is 90 meters long and 7.2 meters in diameter. Flap gates in the downstream manifolds can be lowered to cut off backflow from the lake in case of emergency. The size of the cavern required for the generating hole depends upon the type of plant which it must contain. Reversible pump turbine motor generators require very much less space than separate elements and are also much less expensive. An outlet structure was built at the western end with an outlet tunnel to a stream below. Control valves are regulated by a mini computer which keeps the total storage in both reservoirs constant. Further controls keep levels above a minimum in the lower lake and below a maximum in the upper reservoir. A spillway is provided for protection against catastrophic flooding or failure in the outlet valves. Environmental considerations, such as laying transmission cables underground throughout the length of Wicklow Gap, seeding the sides of the reservoir with grass, and even replanting heather to restore a natural appearance were paramount. Attention was also paid to the design of buildings above ground, such as the administrative building, so that they would blend with the landscape. In the design of the cavern, a saving in space has been achieved by using vertical units. Other advantages are they place the runners conveniently at the low level required for pumping, and since both runners and generators are encased in concrete below the main floor level, noise is reduced. Disadvantages are overall cycle efficiency is less, longer time spent in changeover to pump duties, and some mechanical problems arise from the use of components for double duties. Technical development has been such that overall performance and economics now favor the reversible system. Availabilities of 90% have been achieved in the first 4 years of operation. The spiral case, fabricated from 1.5% manganese steel plate, is placed in position. The complete case and the pipe leading to it were tested to 70 kilograms per square meter. A resilient wrapping was applied to the spiral before it was encased in concrete to reduce vibrations and forces being transmitted into the building. The main reactions are carried into the structure by a collar on the inlet pipe and a deep skirt on the stay ring. High-pressure water entering from the manifold is controlled by spherical valves 1.7 meters in diameter. Each valve is designed to intercept full turbine flow and carry reactions of about 290 tons into its foundations. Together with its operating servo, the valve weighs about 55 tons. A maintenance seal as well as a service seal is fitted so that it is absolutely watertight to allow safe working inside the turbine during overhauls. The operating servo utilizes the penstock water pressure. It is toroidal in shape, a design which transmits its reactions back into the body of the valve. The water to and from the stay ring, which has 12 stays, is regulated by 24 guide vanes. Stay rings are 1.5% manganese steel cast in two halves which were bolted together and welded on site. The 9-bladed runner is about 3 meters in diameter and 80 centimeters deep. It is cast in 13% chrome nickel steel and weighs about 9.5 tons. Blade profiles were determined by model testing a 250 millimeter runner. Because of the load that can be applied to the head covers of reversible machines, special studies were made of their rigidity by model tests and finite element calculations. The resulting design is a prototype and has been most successful in operation. The object is to minimize leakages on the guide vanes by keeping the axial clearance small, while at the same time avoiding vane binding, which may occur if the covers deform under load. On the Turlock sets, the guide vanes have a slipping clutch connection instead of shear pins or bending links to protect the vanes should they close onto some foreign objects. The clutch transfers torque from the vane lever to the vane spindle. Unaffected vanes can close properly, while those which are obstructed can be restored to position when the obstruction has been removed. Stops are provided on the cheek plates to prevent a blade entering the runner area. A test ring was used to demonstrate that the clutch connection can be reset to the predetermined position again and again, always maintaining the correct frictional value. The turbine bearing is a center-pivoted pad type. This provides a closer control over the shaft movement compared with a plain journal over the same temperature rise, hence reducing wear on the carbon seals and increasing the stability of the shaft. The machine torque is transmitted by shafts of manganese-bearing high-carbon steel. Since vertical units do present problems of accessibility, an intermediate shaft can be removed so that the head cover and runner of the turbine can be raised without disturbing the generator. The installation of the motor generator unit nears completion as the rotor is installed. Each unit has a rated output of 87.5 MVA as a generator at 0.85 power factor, and a rated power of 87.5 MVA as a motor at 0.95 power factor for maximum output. The rated voltage is 10.5 kV at the normal running speed of 500 RPM. The output for synchronous condenser operation at 0 power factor, under or overexcited, is about 70 MVA. Class F insulation with epoxy resin impregnation is used for the stator installation, and therefore carbon dioxide fire protection is omitted. Standstill heating is provided to avoid condensation when the unit is off load. The thrust bearing is of critical importance. It is fitted above the rotor and supports the weight of all rotating parts as well as the hydraulic thrust, a maximum load of approximately 200 tons. In non-reversible machines, the pivot is normally arranged behind the geometrical center of the tilting pads in order to obtain an oil wedge. Reversibility requires that it be suitable for rotation in either direction, and the pads are pivoted centrally with chamfers on the leading and trailing edges to get them to tilt. A jacking oil pump delivers high-pressure oil to each pad during the starting period to reduce the breakaway torque. A pony motor, rated 5.5 megawatts of the slip ring induction type with a maximum rotation of 592 RPM, is mounted directly on the shaft of each machine. Its speed is controlled by a liquid resistor connected in the rotor circuit. The pony motor is the only part of the unit which appears above the main operating floor level, and it is used solely for starting up in the pumping mode. A static system of excitation is provided. A constant voltage AC generator mounted on the shaft of the main machine supplies a three-phase bank of 18 thyristors. Two main transformers, each with a rating of 175 MVA, are both made up of three single-phase units. Two large three-phase units would have required greater cavern width and a larger access tunnel, so in this case, the multiple units are the more economic. Another advantage is that one extra single-phase unit can be conveniently stored in the cavern, readily available as a replacement for any of the other six. Each single-phase unit is housed in a separate cubicle at main floor level. This single-line circuit diagram shows all the main features, including the low-voltage supply to the station auxiliaries. 4 possible sources of supply are provided. 2 fireproof unit transformers with automatic changeover, a 1000 kVA auxiliary turbine-driven generator, and a 590 kVA diesel generator. The diesel, started by push button from the control room, is intended for use in emergency, such as the flooding of the cavern. The construction phase is brought to an end with the testing and bringing into operation of the electrical system and switches, the hydraulic system and valves, and the initial running of the main machine. Followed by the synchronizing and loading when the machine starts supplying energy to the system. Thermal plant requires 3 to 4 hours for starting up, compared with 70 seconds for the Turlough Hill machines. In the pump startup sequence, compressed air is used to depress the water below the level of the runner. The pony motor then comes into operation, bringing the main machine from standstill up to rated speed in 3 minutes. The driving torque of the pony motor remains constant up to about 90% speed. From there on, it is controlled by the speed adjusting device in the automatic synchronizer. After synchronizing, water is reintroduced into the runner and pumping begins. The pony motor is switched out and its brushes are automatically lifted to prevent wear. This method of starting up minimizes the electrical impact of bringing a pump onto the system. The normal operation of Turlough Hill from the control room is almost entirely automatic. For standby operation, the Turlough Hill generators can be kept spinning at low load during the day or in synchronous condenser or spin mode, ready for any demand which may arise unexpectedly. Should a loss of generating output occur which would cause a frequency drop, the Turlock Hill machines will counteract the loss immediately. This they do during the night by tripping the pumps, thus throwing the pumping load back onto the system. If that is not enough, the machines will rapidly change over to turbining and pick up. The changeover from pumping to full load generation takes 90 seconds. During the day, the machines running at low load will start to pick up in less than a second and reach full load within 20 seconds. In the total operation, consideration has to be given to the safety and comfort of the operations staff. An escape route for the operators is accorded by the ventilation tunnel at a high level in the cabin. In the event of fire, the ventilation is regulated to provide a straight-through system. For the comfort of the operators, the ventilation system is air-conditioned. The danger of flooding is very remote. A drainage gallery sump collects coolant and water seeping into the cavern, from which 3 to 5 pumps discharge it into the lake. A backup system is provided by the flood level monitoring equipment, which will operate controls automatically in emergency conditions in order to start up the pumps, close the flap gates and the spherical valves, isolate the main electrical network, and start up the standby diesel generator. Since it started operation in 1973, Turlock Hill pumped storage system has proved very successful. Not only does it fulfill its main role by permitting the ESB to operate its modern high-capacity plant most efficiently, but also, in running standby for this plant, the risk of cascade tripping in the event of any large capacity unit on the system failing is avoided. This extension of the original concept has been achieved by modification of the designed control sequences and the development of new operating techniques. In an era of ever-escalating energy costs, Turlock Hill has more than justified the faith and hopes of the ESB staff who designed, built, and now operate it.